Okay, it's recording.
All right. So, good afternoon. My name is Justice,
Oh, I'm Gabe.
My name is Misal.
I'm Kevin.
and today we will be presenting our ME106 project, which is called the Sunflower. So, essentially, our project objective was to design and develop a device that tracks solar light waves to optimize renewable energy production for general usage for the public. So, our design that we decided to go for took inspiration from the thrust vectoring technology in the F-35B fighter jets. As you can see in the video or this little GIF, that the engine nozzle is changing directions from a straight horizontal angle all the way down to a 90-degree. And that's kind of where our inspiration for our design came from. So in our initial design, as you can see, we have a top part with all the solar panels, a body part, which is orange, that contains all of the housing units for both mechanical and electrical components, and a base. So in our initial design, we considered gears to drive the entire rotations of the entire device. But as soon as we got to the fabrication portion of the entire project, we saw that these gears weren't quite what we were expecting. So we had to adjust to this final design where the motors are concentrically in the middle of each connection so that it could properly rotate around the axis of the shaft. Because as I said before, with the gears, there was a little bit of translation, which wasn't quite ideal for our case scenario.
And here we have the circuit diagram. Everything's basically centered around the Pico and the breadboard. We connected the 3.3 volt rail and the 12-volt rail and the common ground. On the left, we have the DC motor connected to the H bridge, which is then connected to the Pico board. On the top, we have the two sensors we use, the UV sensor and the ultrasonic sensor. And on the bottom, we have the stepper motor connected to the stepper motor driver and the power supply right there that has our 12 volts in.
The code here starts by initializing all the pins. Pins 27, 28, 26 are dedicated to the sensor since they are specifically compatible with ADC. So we can read values from them in U16. Then we initialize the motors on 10, the DC motor on 10, 11, 12, 15, 14, so that it connects to the H bridge, and the stepper motor on 18 and 19 for step and direction pins. And then finally, the microsecond delay for the stepper motor. After that, we have, no, on the next slide, yeah.
Oh,
We have the entire functions basically comprised of three functions. The first of which is a calibrate function, which calibrates the sunflower to find where the sun is in the sky. It uses spherical coordinates, specifically rotations along the XY plane and the YZ plane. The YZ plane, like this, is controlled by the DC motor using PWM functions, or rather, never mind, just due to U16 function. It runs at 30% power for 0.2 seconds and then turns off to get 30 degree, 60 degree, and 90-degree angles. After that, it runs a stepper motor and divides the sphere into 10 spots to take that values from, which in total creates 41 values that we can use to find the maximum to find the sun. And then finally, it goes after the sunflower reaches all of these locations, it goes back to its original position. The next two functions are get max and go to. Get max finds the maximum value from that the ultraviolet sensor reads, and then stores that coordinate as the maximum value so that I can find the sun again. And then the go to coordinate takes that coordinate value and then spins the DC motor however many times it needs to, and the stepper motor however many times it needs to get back to the position. And the main code is just those three functions. Calibrate, then from calibrate uses the output to get the max, and then it uses the get max output to go to the sun.
So here's a little demonstration video when we first fabricated the entire device. As you can see that both motors that we implemented are working properly. It's just that the structure itself and the overall stability of it is what kind of hinders the entire device to function properly. Additionally, on top of that, we have the wiring that also causes a little bit of messiness within how the overall device runs. As you can see in the video, Gabe has to move all the components with it as the device turns because of just all the connections and how close they are. But overall, we get the idea that the top motor is able to rotate to adjust for the angle, and the bottom motor is able to adjust the entire device to properly locate and find the sun source.
So as Justice mentioned, so some of the things after the demonstration, we were thinking about how to make it a little bit more stable, or at least the base would be stationary and the top would move. Some other improvements that we were thinking for the future is part structure, probably make it not as tight, and so that it's more serviceable and we can reverse engineer it. So like I said, also like we want to reverse engineer and make it serviceable. So that's why we also have like a way to pretty much we gotta find a different way to package the hardware and the circuitry inside the little capsule. Probably change the motor control where it can be a little bit more like smooth than then instead of just constantly going at 1.1.1 instead we're going to try and make it a little bit more smooth. Future improvements are probably having this capsule or the sunflower be a little bit more mobile, where it can probably move itself and be able to self-sustain while using the sun to self-sustain itself, so it doesn't require a additional power source. And another thing another item that we want to do so that we can make it more which we want to make it more retractable, so it's much more portable as well for the consumers. And I think that is it.
Yeah, so that is the end of our presentation. Thank you for listening.